All right, good morning, everybody. Hopefully, everyone can hear me. Please let me know if there are any technical difficulties. Just check my voice here. Out of paranoia, it seems to be good. Okay. All right, so previously we've introduced the area under the graph y equals f of x. I needed to specify some x values as well, a to b. Let's visualize that. Now we say under the graph, but we really mean between the graph of my on the left by a and on the right by b. This is represented by the definite integral from a to b of the function, and x is my variable. I plug in b, I plug in a, and subtract, where this a of x is any antiderivative of my given function. So we did a couple of examples. Let's just do more examples to cover everything that we need to see. I want to look. Let's focus on something like number 8. Before we worry about the area that this represents, let's just make sure we can calculate a definite integral, and notice that the answer that we get is a number in comparison to the indefinite integral that doesn't have any numbers there. Then my answer is a family of functions. So I have the integral in number 8, 1 to 8, 1 to 8, and the numerator 3 minus x to the 1/3 over x to the 2/3. So now I can't forget that I'm still asking, for the first part of this question at least, asking an antiderivative question. And there's no reverse quotient rule for us, so I need to just rewrite this so that I can see how to reverse engineer this guy. So it'll be 3 over x to the 2/3 minus x to the 1/3 over x to the 2/3. And then I will simplify each of 1/3 minus 2/3 is negative 1/3. Now I'm ready to look at antiderivatives here. Now it's going to be a little bit annoying, but we want to now just cover everything to see how is the definite integral different? What's the same? Is it good news or bad news? I think it's pretty much good news. Now the antiderivative. I don't love the 3. I focus on the essence of the function and then look at what the power rule is going to do to get me to this target. The power rule is going to take some power of x, subtract 1, and then give me negative 2/3. So that has to come from 1/3. Now the 3 may or may not be something you want to incorporate. For consistency, I just always leave it out. Not have that be a part of my argument, because sometimes it works and sometimes it doesn't. And I'd like to be consistent. So I see here that I've accounted for the 3. The power rule is going to put a 1/3 in front. I need another 3 to catch that because there's no other constant in there. Minus, it's going to have to be x to the 2/3 because the power rule is going to decrease that by 1 to get me my target. I don't see any other number. I'm going to have to put a 3 over 2. That's actually 3. I'm going to have to put a 3 over 2 in front to catch that. And once I'm happy with my antiderivative, it might be a good idea to simplify it because now I have to plug in the top boundary value. So I'll have 9 times 8 to the 1/3 minus 3 over 2 times 8 to the 2/3. All of that minus what I get when I plug in a 1, which is 9 times 1 to the 1/3. Now I know that simplifies. I'm just emphasizing that we have to plug it in this way. 3 over 2, 1 to the 2 over 3, like so. Now I'm going to leave it to you to calculate these answers. And please let me know if you calculate it again, and you get different answers every time. Something's not happening, you're not sure. But in order to save time, this is basic calculator stuff that you should be able to do. I'm focusing on the new aspects here, and there isn't much. There's just a calculation step that's attached to my antiderivative question. All right, so this is a pretty straightforward situation. We just want to be extra careful to calculate this last answer correctly. All right, let me see if I have space here. No, not really, huh? All right, let's do number 7. Integral from -1 to 0. -1 to 0. X times bracket to the power of 5 2x squared minus 3. 2x squared minus 3. All right. Now, pretending these numbers aren't here for a second, what kind of situation am I in? Yep, I'm in a substitution situation because I have a function of a function. Okay. So the fact that I have some numbers here, making this a definite integral, doesn't change that fact. Now I have two ways to go. I'm going to do this way first to make it as relatable to what has come before as possible. First, I am just going to look for an antiderivative. Oops, sorry, exactly the opposite of what I want. Just look for an antiderivative. That means without the left and right boundary values, making it a definite integral. Because this definite integral question comes in two parts. Find the antiderivative, then plug in the numbers. So let's go and find the antiderivative first, which makes this an indefinite integral. Well, now I recognize this is substitution, so I'll choose my substitution as the obvious one, which is correct. Then take the derivative, just like always. I get 4x Then separate the differentials so that it tells me what I need to see. And I see that, ooh, I'm missing a 4. Well, okay, let's just fix that. Bring in a 4, but pay the price. Then everything is going to still be equal. So now I have my 1 over 4. I'm able to rewrite the whole integral in terms of u as u to the 5 and du. I can then easily find an antiderivative as u to the 6, 1 over 6. Now I don't care about the constant because I am coming back. You're welcome to write a constant here, but I am coming back to my definite integral issue, which doesn't care about a constant because I just need an antiderivative. So I'm going to take the simplest one. So I'm going to simplify this now as 1 over 24 because I have a further step that will follow this one. Go back to x's. U is 2x squared minus 3 and now to the power of 6. So now I can say that, let me just make some space here. Now I can say that my definite integral original question, which was this one, is an antiderivative, which I found separately with a -1 and a 0 plugged in. I will emphasize once again that we are plugging it in. Plug in the top value, 2 times 0 squared minus 3 to the 6, minus, plug in the bottom value, whatever that may be, and then we will get the answer. Now it might be beneficial in this case to get an answer. Our calculation isn't super uh, messy. So let's just get the answer because I want to verify the other way that I'm going to do it is going to be the same. So I'll do that in MathBot as my calculator. Let me just double check. Hopefully that is what you got as well. Let me know if it's not. I have 1 over 24. And then I simplified the bracket because of the 0 is just a -3 inside to the power of 6 minus 1 over 24. I simplified that bracket because -1 squared is 1. So I have 2 minus 3, which is -1 to the power of 6. Okay, it looks okay, but let me know. Everyone can make a calculator mistake very easily, especially if you're trying to do it quickly. Let me erase my little dots here. We get 30.33. It's really hard to know when you do a calculation, did I do it right? You can do it again, you can confirm it with someone else, and that helps. But in a test, it's definitely something I want to take my time with and be careful that I get the right answer because now the answer actually matters as a numerical final answer. Okay, so there's absolutely nothing wrong with this method. Let's zoom out and see the whole thing. Nothing wrong. And for the longest time, I did it this way, unless things get super complicated in my original function, making this a little bit messy. What's the pros and cons here? Pros and cons. The pro is that I'm very much doing a familiar antiderivative indefinite integral question, even though it's substitution. I've done this first part before. I then just come back and plug in the numbers, and it's just a little calculation. So the pro is that it is fairly familiar. There's nothing really new here. It's just the second calculation step. But often with substitution questions, my antiderivative answer here can be quite long, where previously I didn't really care because that's where I stopped. Now I kind of do care because a long function here will present potential difficulties when I calculate, which I do have to do. So what else could we have done? Let's zoom in. We could have said, okay, well, let me keep it exactly like this. -1. Let me not do an indefinite integral. Let's keep it as a definite integral. And then do derivative du dx, get 4x, separate the differentials, 4x dx, and so on. I have the same issue that I need to see a 4, so I'm going to pay the price to bring in a 4 so that I'm able to get rid of all the x's as I should. So nothing's. So I get a u to the power of 5 and I get a du. But the problem now is I don't have a -1 and a 0 anymore because what this 0 meant as my upper boundary was really x equal to 0. X goes from -1 to 0. And if I'm going to change the variable from x to a u, I need to figure out if x is -1, then what is u at that same point? So I plug it into my substitution and get -1 for x, so the squared is a 1, so that happens to be a -1 as well. But if x is equal to in terms of u, if I'm going to go substitute the definite integral, I have to do everything involving x and change that to corresponding information involving u, including the upper and lower boundaries. But that has a benefit to it we'll get to in a second. Let me finish this. I have my 1/4 in front, antiderivative, which is in u, and I'm going to plug in the corresponding numbers for u, which means I have 1/4, which technically stays out in front, I suppose, 1/6 -3 to the 6 minus 1/6 -1 to the 6. Now feel free to pause here and calculate and verify that I get the same 30.3. And if you look, this essentially looks the same as before. So I'm going to get my same answer. The issue is, well, let's look at pros and cons of this. And there are some. Con is I can very easily forget or miss the fact that my original boundary values were linked to x. And if I'm doing a substitution, that's only going to be successful if all x-related things are converted to u's, u-related things for my new variable. That includes these boundary values. So I have to change them as well. So there's a little more to remember. But the big pro is that in going to a variable u, I have simplified my integral and my antiderivative, and therefore my calculation significantly. Now, it might not seem significant in this case, but for many substitution questions, the antiderivative answer in terms of x versus the antiderivative answer in terms of u has a big gap in complexity, which makes my calculation step easier. So it's always your choice. Which one do you want to go completely in terms of u? If you just have to solve it, you can choose how to approach that. Let's just do one more of this to highlight the choices that we have. Let's see, which one do we want to do? I might as well do number 9. Why not? Number 9, root of log of x over x, and my integral is 1 to 3. All right, so now I can choose. So let's do them again, side by side. And remember, we're only choosing one. Know your options, choose which one you are most plugging it in. Separate these two parts. Well, that's going to need a substitution. Let u be natural log of x. Then my derivative is obviously 1 over x, which I perfectly see. This third part separating the differentials, just verify what I need to see, and then I'm ready to do it as root u du. Now that's u to the 1/2, which I can do a reverse power rule on as u to the 3 over 2 and 2/3 in front plus c. This method requires that I go back to x. It's going to be natural log of x, all of that to the 3 over 2. Then, going to my definite integral, I've now found antiderivative, which is 2/3 natural log of x 3 over 2, which I'm going to plug in a 1 and a 3, and it's therefore going to be 2/3 log of 3, all of that to the 3 over 2, not just the 3, minus 2/3 log of 1, all of that to the 3 over 2, and you're welcome to calculate that answer in your own time. Nothing that we can't do. We relate it back to what we've done previously and just put a calculation step after that. The alternative is to stay with the definite integral when I do the substitution and say same substitution, because it is essentially the same antiderivative. Well, it's exactly the same antiderivative. So not much has changed there. I'll just write it down again. Then I see, oh, there's no adjustment necessary. I'm good to replace this completely. as, again, root u du. But now the 1 and the 3 refer to x. So I'm going to have to replace them as well. The bottom one is going to be log of 1. Top one is going to be log of 3, which you can keep like that or use a decimal, do whatever you feel comfortable with. I then have now everything is in terms of u. So I can move forward finding an antiderivative as u to the 3 over 2, 2/3. And I'm going to plug in log of 1, log of 3. Let's just finish it. Now you might have decimals here, but I'm going to leave it like that to show that what I get as a calculation is exactly the same. You decide which one is safer for you. You can see here they are identical. In many cases, the left side is a little bit longer because I have to go back to x before I can do my calculation. The right side doesn't have that drawback, but I do need to remember that I have to change the left and right boundary values. So there's no one clear winner. Um, be aware of both, just in case the question specifically instructs you to do one or the other. But if it doesn't, you can choose which one you want to do. So that's really the worst case with a substitution on top of a definite integral. Let's now go back to the area concept that is linked to this definite integral. We said that the definite integral a to b of my function represents the area under the graph f of x on a to b. And we visualize it, a to b. There is my, whoopsie, not that bit. There is my function, good times to come. But let's look at an example. What if I want to find the definite integral, let's say -1 to 1 of x cubed. Now, I can graph this, but let's pretend this is coming from something more complicated, and I don't even know what the graph looks like. I don't want to spend any time to graph it. What does this give me in terms of an area? It's just an area calculation, right? So let's just do it. I'm just picking a simple one that I can graph after this. Well, antiderivative, x to the 4, 1 over 4, -1 to 1, which I'll then plug in, 1 to the 4 minus, plug in the -1 to the 4, and what do I get? I get 0. But there is a graph, and there is a space between the x values, so surely there is an area. What does this graph look like? Well, the problem is that this graph has, on this interval, a portion above and below the x-axis. And what this definite integral is actually doing is a little bit more fancy. It's actually associating a sign of positive with areas above the x-axis and a negative sign with areas below the x-axis. And when they're put together, there is a cancellation in positive and negative areas that happen automatically. Automatic. Now, before we had such simple examples where we picked a graph and an interval that was well above the x-axis, and there was no issue. The area was positive already. Then the definite integral does represent the area under the graph if that graph on that interval sits well above the x-axis. But in more general situations, I have a crossing of the graph over the x-axis, creating an area above and an area below the x-axis. And the integral here really represents the net area between the graph and the x-axis. And unfortunately, that is built in. It's built into the definite integral. It's the way it's technically defined, and there's not much I can do about it. But be aware of what it truly represents. So if the question just asks me, find this definite integral, well, then I don't really care about the area that it actually represents. But if it's asking me, let's make a new page here. If it's instead asking me to find the total area between my graph and the x-axis on -1 to 1, then the answer isn't 0. I would have to calculate this area and then add them up. Let's suppose you have an area of land that comes in two sections. And the way it's set up, if you represent it mathematically with an x-axis as a straight line, has this situation. You can't go to the government and say, oh, I have 0 land. My area is 0. No, you have land and you need to pay taxes and whatever. But it's because of the setup, the definite integral as a one-time calculation does not separate these positive and negative areas. We have to manually do it. Now the intersection, the crossing here happens at 0, so I have to manually separate from -1 to 0, calculate that. From 0 to 1, calculate that. Now the antiderivative is going to be the same, so it's not two completely separate ones. This is going to have the same antiderivative, but I plug in different values. This one on the left is going to require that I plug in a 0, subtract, plug in a -1, and what am I going to get? I'm going to get negative 0.25. The negative, because I know what the graph looks like, negative makes sense. That simply means the position of the area. It doesn't change the size of that little area, that little wedge type shape. The negative just indicates the position. And if I now want to calculate the total area, I need to just separate position from actual size. The one on the right, well, we secretly know that does sit above the x-axis. As long as I don't cover too much with my x-interval, isolating just a top portion, just a bottom portion, then the cancellation risk is avoided and I get a positive 0.25. Now, because of symmetry, they're the same. I can then say the total area is top 0.25, area 1 here, plus the bottom 0.25 from section 2, if you will, to get a total area of 0.5. If I did this in one go, essentially the definite integral will just add these with their signs, and it seems like the area doesn't even exist. There's a cancellation that needs to be avoided. So how do I spot that? When and where do we need to split it up like this? Do we need to split the interval? When I have an x-intercept inside the interval. Or let's say here at an x-intercept inside the given interval. So that's always going to happen. If I have a graph regardless of what it is, if in my interval there is an x-intercept, that means it's going to cross the x-axis potentially. And some area might be positive, some area might be negative, and if I do not split it up here at this x-intercept C, my full one-time definite integral is not going to accurately give me the total area between the graph and the x-axis. It's going to cancel some stuff because built into it is this positioning of the area. So the area A to B of my function is a signed area. It's built in. I'm not going to change it. It's the way it is originally defined. But if I'm looking at an area question, then that sign is going to get me in trouble because of this cancellation possibility. So I need to manually avoid that. So let's see how that would look in some examples. Looking at the area questions, and you see there we have a whole bunch of them. We'll worry about the two graphs in a little while, not today. So let's pick something. It doesn't really matter, right? We've done x cubed, so that's maybe a little number 6. Let's go with number 6. Why not? Number 6. I'm looking for the area between my function is x cubed minus 2x, negative 2 to 4. X cubed minus 2x, negative 2 to 4. So now I'm not going to bother necessarily graphing this perfectly, spending a lot of time. All I need to check is what are the x-intercepts of this guy, where I set y equal to 0, and I need to solve for x in the resulting equation. So now I can factor out an x to get x squared minus 2 in the bracket. So that means I have x equal to 0 or x equal to plus minus root 2. Interval. Well, I need to go check what is the square root of 2. Square root of 2 is roughly 1.41. So we picked a big one, but it doesn't matter. I'm not going to have just one x-intercept. Whatever x-intercepts fall in here, they happen to all fall in here. So if I'm going to break up, let's do it graphically. Now I don't know. I'm going to go negative to 2, negative 2 to 4. I don't know what my graph does. All I know is there is a crossing at 0. There's a crossing at negative root 2, which is negative 1.4, which still falls in here. And there's a crossing at, potentially, at root 2. Now, I don't care what it looks like. It doesn't really matter. I could have a graph up here going like this and then turning, something like that, which means I'm going to have negative areas, positive areas, negative areas, positive areas, and I need to isolate them all in order to find the total area. It doesn't matter if there's just one section, if there are 10 sections, it's all the same, regardless of what the graph looks like. The x values, so the x-intercepts that fall inside my interval need, they tell me how to separate the given interval. So let's do that. So my function is x cubed minus 2x. So tedious as it is, there's no way around. I have to calculate negative 2 to negative root 2 of my function, x cubed minus 2x. Then I have to calculate negative root 2 to 0, but it's the same function, so the antiderivative is going to be the same. It's just a calculator hassle, really. Then I have to calculate 0 to negative root 2, not negative, positive root 2. Same function. And then I have to calculate root 2 to 4. Same function. Now I don't know going in how many of these splits will have to occur. I have to find the x-intercept, and that tells me, oh, there are 3 of them in this interval. Fine, let's do it. This is really worst case. But notice that the antiderivative is always the same. I have 1 over 4 x to the 4 minus x squared. I'm going to plug in these numbers. Antiderivative, always the same. Just the numbers that I plug in will be different. Antiderivative, always the same. Different numbers for each one, which will of course give me a different answer. Antiderivative, always the same. Yes, it is tedious. Yes, it is annoying. It is the only way. So I'll calculate, let's calculate some of these. Why not? I'll calculate a couple, and then let's suppose here we get 1, 2, 3, 4 different areas. Some of them are going to be negative, some of them are going to be positive. Let me calculate the first 2 for you in our last 3 minutes, and then you can do the rest because it's just calculator work. So the first one, Maybe we'll just calculate one of them. So it's quite tedious and we're running out of time. So I'm going to do the plug in the top minus plug in the bottom, just so you have, um, whoopsie, a more broken up version. So when I plug in the top boundary value, I get a -1. Then I still have to subtract what I get when I plug in the bottom one. Now I have not cared about the negatives because my powers of x are even. It's going to get rid of the negatives. Oops, I need to put an equal sign in front. There we go. We get a 0. So my answer for this first one is -1. You'll then get an answer here. Answer 2, answer 3, answer 4. Make them all positive. Zoom out. Make them all positive, and the total area is the sum of positive, so absolute value of answer 2, absolute value of answer 3. Make them all positive. It's just a little tedious to do, but there's no deep insight involved. I have to separate. The next one's going to be positive. The next one's going to be negative. The next one's going to be positive. And if I do it all in one go, I get a number, but that number means nothing in terms of how much area is actually between the graph and the x-axis. I can't use that simple definite integral at all. I need to separate it like this, whether I want to or not. So we'll do a couple more tomorrow and continue our area discussion. But for now, you can, let's zoom out here. You can look at all these problems, area between the graph and the x-axis. You can just practice definite integrals and any catch-up you need to do. So we'll continue this discussion on area tomorrow.